All right, so let us talk about the history of deep learning and let us talk a little bit about natural language processing. Um, First of all, we want to, in the beginning, neural networks were introduced as a metaphor of the human brain. You can see that metaphor graphically visualized here. You see a human brain that you can think of as consisting of different so-called neurons, which are connected to each other via weights. And if you have such a picture in mind, you can also see in this depiction of the human brain, well, you can also see the idea of neural networks that is deduced from such a imagination of the human brain, namely that you have different units that are connected, and maybe these units fire depending on whatever input comes into them. So this was the 1940s. This was the initial motivation for neural networks and perceptrons. Then in 1958, we already talked a little bit about that. There was Frank Rosenblatt that had, a paper or a book on that, which gave several properties of these perceptrons, what they are able to do. But then also later on, I think the same person criticized these perceptrons for their limitations, especially for the most popular case is that they cannot solve the XOR problem. That led to an awkward silence, AI winter, which also hit neural networks pretty heavily. People were basically not using them because they were considered to be very limited. Even though we had this deep winter which lasted for a long time, we did see some progress, some big milestones. For example, in the 70s and 80s, backpropagation was developed. This is an algorithm to train deep neural networks, which would work in principle but did not work in practice for a long time. And also, like in 1998, Jan LeCun, pictured here, had a convolutional neural network, which is a special type of neural network, recognize handwritten text, which was also a milestone. But basically, even though these individual milestones existed, neural networks were not the most popular technique, and other techniques instead had the upper hand. For example, support vector machines, you may have heard about that. They were like dominating the 1990s and also the 2000s. And then things started to slightly change around the middle of the 2000s. First, this can be attributed to individual successes again. For example, 2006, Geoffrey Hinton, which you see pictured here, had a paper where he showed that if you do pre-training, if you find good initial solutions for these neural networks, then they can work better. And I also had another paper on the restricted Boltzmann machines, which was also a kind of model which could do fancy things. But the second contribution why neural networks became popular again was that some people, including Geoffrey Hinton, thought that a better advertising strategy was necessary. So what they did is they changed the name from neural network, which was very unpopular at the time, to deep learning, which sounds much fancier. Um, this strategy also helped to increase the interest in neural networks and in then called deep learning. And then around the 2000s, we saw real breakthroughs. So, for example, 2012, Google Brain started, and also in 2012 there was AlexNet, which was a neural network, a kind of neural network, a deep neural network with many hidden layers that won ImageNet. So this is an image classification task where you have to label images according to the objects that are in there. And for the first time, a neural network could win this competition. And from then on, there was also big breakthroughs in natural language processing. So this is our core field in this course. So for example, 2013 we had Thomas Mikolov and the so-called word-to-vec model, which many of you may already know. So this is a model that maps words into vectors, and it has very strong properties, and it gives good representations of words. And that was the breakthrough in NLP, and from then on, the whole field changed. So everybody was switching basically to neural networks, and nowadays almost nobody is using anything else than neural networks in our field. And like the highlight, so to speak, was just last year when Hinton, which you see here in the middle, Joshua Benjo from Canada, Jan Lecan also from Canada, Hinton is from Great Britain, when they won the Turing Award in computer science, which is the equivalent of the Nobel Prize. So this was really a major achievement and recognition of their work and of the impact that deep learning had already, and it is likely to have in the future. There's also a big German guy who is working in Switzerland. His name is Schmidhuber. He was the inventor of the LSTMs also back in the 1990s already. At the time, this was just theoretical breakthrough, but only much later did people find out that these models are actually quite useful, quite good, and they were the state-of-the-art models until just recently. But unfortunately, or however you want to call it, Schmidhuber did not get the Turing Award, even though several people say he would also have deserved that. So what can we say about the successes in image classification? So we already talked a little bit about AlexNet and how it won. So what was the situation before AlexNet? Here you see this ImageNet classification task. Again, the task here is there are pictures, and the computer has to decide which object is displayed in the picture. So the objects could be animals like cat, dog, elephant, or like a car or a human or something. And before neural networks, like in 2010, 2011, we had like traditional approaches, and they had like decent error rates, not too bad, not too good either, like between 20 and 30% error rate. Then in 2012 came AlexNet, and for the first time there was a neural network beating these traditional approaches, and from then on it went quite quickly. So like within a few years, the human accuracy level was achieved and then even surpassed. What do we have in natural language processing? Well, our major toolkit, so to speak, is machine translation. So this is translating from one language to another language. You certainly know the most popular such toolkit. This is Google Translate. The task is, as I said, translate between two languages. Could be English or Spanish, English, French, English, Chinese, Spanish, English, French, English, Chinese, English. So there's also a matter of direction. Do you translate into English, from English? Of course, also other languages than English can be involved in machine translation. So here we see the quality measured in some ranking. What we had from the 1990s to 2000 to the 2010s was so-called phrase-based machine translation. That worked decently, and people spent a lot of money and a lot of effort and resources into that for 20 years, and it worked to some degree. It was still very limited. Machine translation output was still very limited. Then came neural networks starting from around, let's say, 2013, 14, until now, and in a few years they almost they are nowadays claimed to be close to the human performance level. Of course, then also it depends which humans do you take as a reference. Usually these are not professional translators which are taken as a reference, but maybe just ordinary bilingual people like for example me or you. But still, nowadays one can really say, and you certainly have tested that and checked that Google Translate works quite well for several language pairs. So under which conditions does deep learning work? So it's often claimed that data is important, size of the data is important for the performance, like for the accuracy scores, for example. And like here we have three different machine learning models. One is traditional machine learning, where we have, for example, linear models, etc. And these are claimed to work quite well when we have just little data. But then as we increase the data, the performance does not really increase. And what is claimed nowadays, the deeper your neural network, like here shallow neural network, that would be probably a perceptron. Or maybe it would be a multi-layer perceptron with just one hidden layer. Then medium would be more hidden layers, and deep would be very many hidden layers. So what is often claimed is the deeper your network, the more data does it need, but the better can also be your performance. When does it not work? As we've seen, like small data scenarios, that's often considered not to be ideal for neural networks. Then there's also the problem of the domain transfer. Like when your test data is very different from your training data. Imagine you have your neural network, you train it on news corpora, you want to apply them to Twitter. Then obviously that's a big change in distribution. Also, humans are affected by such changes. So if you would all the time read only Twitter, then you'd probably have problems understanding a more high-level conversation. So even humans, even humans have problems with domain transfer, domain change. But in particular, neural networks also have this, and all machine learning classifiers do. But there's some insight that maybe neural networks are a little bit more sensitive to such change of domain than other classifiers. And in particularly, they can be adversarially attacked. So what is that though? Like in 2014, 2015, Ian Goodfellow had like a seminal paper where he showed that if you have a neural network and it's performing some task. For example, it would do image classification and we have to classify that this is a pig. Then you can choose some small noise that is almost invisible to humans. So you have this small noise here. You just take a little bit of that noise and you add it to your original picture. You get a different picture which is basically identical for humans to the first picture, but your neural network would classify that totally differently, right? So why is that? So there are different speculations why that is, but one reason is probably that neural networks do not learn at least at the moment in the same ways that humans do. So they do not make the same representations of the data than humans do. So humans may use high-level logical inferences, while maybe neural networks do exploit very low-level statistical cues, and these low-level statistical cues could be that's sometimes called a dataset artifact. For example, if you want to classify whether a string is a person name or not, a neural network could find that whenever a opening bracket follows that name, then maybe this is a human person, because in newspaper text, for example, they often write the year of birth or the party affiliation in brackets, and the neural network could learn such very low level cues instead of making more deeper and richer semantic connections. Like if the verb has a special form, then the subject has to be animate, so it has to be a human. For example, eating a car can usually not eat unless you're using a metaphor. So humans might build such connections, and neural networks might not build such connections. So from deep learning, let's go to natural language processing. So in natural language processing, we have three model tasks, three basic tasks, so to speak. So the first basic task is so-called classification, sentence or text classification, and in this case we have a sentence or a document, and we want to classify that into different labels. For example, if we have a sentence like "I hate this movie," then maybe you want to classify this as a sentence that utters negative sentiment. And this is important, especially like for several industry players such as Google, Amazon, or Facebook, also because they want to declassify the huge amounts of data that they have. For example, also could be relevant for Facebook, who want to classify um, their commentaries and their conversations into whether they are racist, sexist, or other things, and then maybe they want to eliminate that. The other model task that we have is called sequence tagging. There, instead of giving one label to a big unit, such as a document or a sentence, we want to label each unit in the sequence. So we would want to label each word in the whole document or in the whole sentence. Uh, and a model problem within this class is to like do part of speech tagging. Like part of speech tagging, part of speeches are word classes. So word classes are something like verb, determiners, noun, adjective, adverb, and we would then want to label each element in the sequence that we have with exactly one label. Um, and the third model class that we have is the so-called sequence-to-sequence model, or sec-to-sec. This is the most difficult problem type. In this case, we want to transform one sequence, like the English sentence, into another sequence, and this could be a German sentence. And in this case, we would call this machine translation. So the problem would be to transform "I hate this movie" into, for example, "diesen Film, ich hasse ihn." And you will also notice that this not only does it have a different number of output units, so you have 1, 2, 3, 4, 5, 6 units here, while in English you only have 1, 2, 3, 4. So this is one difference to sequence tagging. So we transform 4 units into 6 units, where here we transformed, so to speak, 4 units into 4 units. And the other thing is that the ordering is may not be preserved at all. So here you have a totally different order than in the English input. So these are the three model types that we have in natural language processing. And if we want to connect deep learning with natural language processing, then what we could look at is what kind of fundamental questions do we have in deep learning, and how do these fundamental questions relate to our fundamental problems that we have in natural language processing. So the two fundamental questions that we have is which neural network do we use? So we have already seen two such neural networks, namely the perceptron and the multi-layer perceptron. There are others that we will come to learn in this lecture. One of them is the recurrent neural network. Particular cases are LSTMs and GRUs, a convolutional neural network, and an encoder-decoder model. And the second fundamental question that we have is, how do we represent our input? And the answer to that question will be embeddings. And we will learn about these embeddings in later lectures, and also in these lectures in the next couple of slides. But before we talk about them, let's map our three fundamental problem types in NLP, namely sentence or text classification, sequence tagging, and sec-to-sec models, to our neural network architectures. And what we could typically use is, for classification, we could use a perceptron or a multi-layer perceptron or a convolutional neural network. For sequence tagging, we would use a recurrent neural network. And for for sequence-to-sequence models, we would use an encoder-decoder network, which consists of two recurrent neural networks, or extensions of recurrent neural networks, such as transformer models. Good. But let's now talk about the input representation. What are our input representations? So they could be characters, they could be words, they could be sentences, or they could be whole documents. And so this could be our input. How shall we represent our input? A neural network always takes a vector, so like a sequence of real numbers as input, right? Doesn't take symbols as inputs, or it doesn't take discrete symbols, but it takes like vectors as inputs. So what should these vectors represent? So we want them to represent at least two things. Typically, the meaning of the units. Like this is called semantics. So what do these units mean? And also, we want to incorporate these representations, grammar, morphology, or syntax. So like this is the form or the structure of the data. And our goal would be, if we have a representation of the input of two input objects, then if these objects are similar, they should have similar representations. And what is the most classical situation? The most classical situation is that we are dealing with words, and that we represent the meaning of these words. And how do we do that? So one of the first neural network architectures, and one of the most revolutionary ones in the context of deep learning, was the so-called word-to-vec model introduced by Thomas Mikolov around 2013, 2014. And this is the visualization of the model. So we will come to talk about this model in much more detail in lectures. In lectures 4, 5, and 6. And yeah, so here are some details, like we use one-hot vectors. Yeah, and to discuss a couple of technical details of the word-to-vec model. So how does it basically work? Like, so there are two different architectures. One is called SIBO, skipgram, and jointly together they are called word-to-vec. And what these two architectures do is basically, given some word and some text, they want to predict the surrounding words. So, or the alternative is, given the surrounding words, they want to predict the word in the middle. So this is the task they want to solve, and the way that they do this is they start out with discrete representations of words. For example, the cat could be the second word in the alphabet, love could be the fourth word in the alphabet. And then so this is also a neural network. In this neural network, they learn a so-called embedding matrix E. So this embedding matrix is here. They learn this, they train their neural network. And as you see, a one-hot vector comes in, and if this one-hot vector is multiplied by this embedding matrix, then we get out exactly the corresponding vector at the index that corresponds to this word. So we would get this vector, so the fourth index, so we would get the fourth row of this matrix, and this fourth row is exactly is then the vector representation of the fourth word in the vocabulary. So yeah, that's what these models are doing. They are training. They are trying to solve a specific task, namely, from given a word as input, predict the surrounding words, or giving the surrounding words as input, predict the middle words. And once they have solved this task, the task is not important anymore, but what is important is the vector representation. And why this model is a good idea to model it exactly in this way, we will learn in lectures 4 to 6. But here you should just get the high-level basic idea that we, as a byproduct of solving this model, we get a vector representation for each word. And what has been shown empirically is that these vector representations are good in the following sense. Namely, we have observation number one, semantically similar words, so words that are intuitively considered to capture the same meaning. They are near this vector space. And observation number two is also that syntax and morphology, or their properties, are somehow also encoded in the vector space. But we'll focus on semantics now. For example, that could be a representation of the vector space in a two-dimensional projection. So usually these vector spaces are at least 300 dimensional, but for visualization purposes we now plot them in a two-dimensional space, because humans cannot go beyond r to the 3. So, and what we would typically see is that you see obviously words that have similar meaning, for example battery and charger, or paint and color, or oven and refrigerator. So intuitively you would say that these words have similar semantics, they have a similar meaning, and we find that indeed these words end up close being in this vector space. And the cool thing is we can even do this across 2 languages, or across 3 languages, or across 300 languages. And what we then see is not only that words within one language are close to each other, words that are intuitively having a similar meaning are close to each other in one language, but also across languages. For example, we would see here Vater and man are close, Id and Essen are close, and Gabel and Essen is close, and Trinken and Trink is also close. Yeah. So you can generalize this across languages, which is a really cool thing, because then you can go beyond the specifics of a particular language and just do global natural language processing across all possible human languages, ideally. And the most fancy current techniques in this context are so-called contextualized embeddings. So in the previous approaches, and these contextualized embeddings, they came about in around 2018 with a model called Elmo. And here you see these people from the Muppet Show, Elmo and Bert, or maybe this is Elmo, I guess, and this is Bert. What these models differentiates them from the previous models, such as Word2Vec, is that now, depending on the context, each word gets a different embedding. So the previous approach had that each word has exactly one embedding, and this results to obvious problems in case of a word having multiple senses and multiple meanings. For example, the word can is given here in 2 sentences, and you see that it's used very differently. In one case it's a verb, in the other case it's a noun, and it has very different meaning. But the old models, like Word2Vec, they would give the same vector to these models. But now these contextualized embeddings, they give embeddings based on the context. And they have become super popular after 2018 with Elmo first. And then quickly after Elmo came Bert. And Bert is even much better than Elmo. So, but I think nobody's using Elmo anymore. So Elmo was very short-lived, just like half a year or at most 1 year. After that, right away, everybody used Bert because it was super powerful, and it also changed a little bit the way that natural language processing is done. And we will hear more about that in lecture 5, I guess. Okay, so this was the input representation. So we have these embeddings, they capture semantics, they can be static or contextualized. About architecture, so we have one architecture that is very popular in image processing, and this is called convolutional neural network. This has a so-called translation invariance. So translation has nothing to do with machine translation here, but like with the property of location of an object. So an object could be located differently across an image, for example, but still the image should be classified the same. So no matter where you see these eyes and ears here and the nose, you would say this is a cat. So it has so a model is good if it can give the same classification no matter where the object appears in the picture. And convolutional neural networks, they have a built-in translation invariance because they do so-called parameter sharing. So in standard neural networks, all the weights can be adjusted, they can be adapted, so you can learn to change them independently of each other. But in a convolutional neural network, you have weight sharing. So some weights always stay the same. So they are jointly. So if one changes, the other also changes. And this reduces the number of parameters and leads to this translation invariance also. So more to the natural language processing side, what we have been using, well, let's say at least until 2018, 2018 were so-called recurrent neural networks, because in natural language processing we often have sequential data, so temporal data, so to speak, because words appear in a sequence, so you naturally have a sequence. And often we want to classify each element in the sequence, right? So we have temporal data or sequential data. We want to do a classification at each time step, so to speak. And the classification usually depends on the history. So whatever what you have seen earlier influences your decision, how you would label some current unit at the current time step. And the RNNs are the standard workhorses for such data. And because we have many such tasks, we have like part of speech tagging is a classical task in NLP that requires to label each element in a sequence, also named entity recognition, where you have to say whether this current word under scrutiny is a person or is a what else could it be? Is it an industry or is it nothing of those things at all? So this is named entity recognition, and this is also a classical sequence tagging problem for which RNNs can be used. So how do they look like? So what we've seen before here is we have seen a standard neural network. We have like a multi-layer perceptron where we have input, we have one hidden layer, and then we have an output layer. And and then in this output layer we do some classification, we give a label. And recurrent neural networks, as the name already suggests, they have a recurrent connection. So the hidden state feeds back upon itself. What does that mean? So it means it is informed by the previous hidden state, and you can unroll such a neural network in time. So this is the equivalent representation that's called unrolling. So at each time step you have an input, I can see. You have the hidden states at each time step, and you see that these hidden states are informed by the previous hidden states. And because they are informed by the previous hidden state, if you are up here, you get information from this hidden state, and this hidden state is informed by this word. So when you are here, you do not only have your current word as input, but you are also informed via this indirect direction about information that is one time step past. And of course you can go back. And because this hidden state is also informed about its previous hidden state, you're also informed about two time steps past, what has been input 2 time steps past. And of course you can go back infinitely long, so you really have the whole history at your disposal when you want to make a new classification. So when you want to classify this can here, then you have the whole history at your disposal, and you know that the context here is I, and if a pronoun or like if something like I precedes the word can, then it's much more likely that this is not a noun but that it is actually a verb and in particular an auxiliary verb. Good, then finally the third architecture is an encoder-decoder model. As I've said, they're ideal for mapping an input sequence to an output sequence, which can be of different length, and the order of the elements can vary. That's in machine translation between languages that are not closely related. And encoder-decoder models, like also up until 2018, they consisted of two RNNs. How do these architecture look like? So we have one RNN here, and we have another RNN here. So these are like slightly modified RNNs. So the first RNN does not have an output. The second RNN does, so to speak, not have an input. What the first RNN is doing, it is representing the input in the hidden state. So like it takes the input and then it represents all of what it has seen in this final hidden state, and then it's feeding this final hidden state in the initial hidden state of the second RNN, and this second RNN starts to generate output tokens based on this hidden representation. So it starts to generate the first one, then the second one, the third one, and it generates as long as it has not encountered an end of text symbol. And we could translate a German sentence into an English sentence with such a model, like sie mag Katzen gerne, into she likes cats. Now, beyond these classical architectures, we have seen a couple of interesting extensions in recent years. For example, we have seen multitask learning in the context of deep learning. That has also been popularized very much in natural language processing. In multitask learning, instead of learning only one task, at one point in time, you learn multiple tasks at the same time. And this is also very much like humans do. So you might learn several languages at the same time, or you might do several computer science courses at the same time, and you do not do them independently. But actually what you learn in one course is oftentimes very helpful for another course also. And this is the idea of multitask learning, that if you learn tasks jointly at the same time, you get spillover effects such that you're informed by the other tasks, and this makes your model better. So this has been a trend very much under focus until like between 2016 and 2018. Now at the moment people have gone slightly different ways, but I think this is very promising idea and will also probably be very influential in the long term. And another cool thing that has come up in recent years is adversarial networks. There the idea is that you have two networks that compete against each other. So you induce a competition situation where one network is generating something, like it may be generating an image, and then the other neural network has to decide whether this is a real image or whether this is a generated image. Like, is it an image that has been photographing a real human, or is it a made up, a fake human? And you can imagine if you have these two networks competing against each other, it's like two adversaries that compete against each other, like police versus counterfeiters, where counterfeiters are in German Währungsfälscher. So these are people who try to make fake money. And these counterfeiters, they generate fake money. And of course, if police is quite bad, so this is the second network, is if that police is quite silly, they can also make money that is also very silly, right? So that is not really convincing. But if police is good, then also the counterfeiters have to be very good. So if police is clever, the counterfeiters are clever, and they try to outsmart each other, try to be better than one another, and over time they reach an equilibrium where the counterfeiters are just producing fake money that is indistinguishable from real money. And so this is the metaphor. And as a result, we get a neural network that is really generating output that cannot be differentiated and cannot be distinguished from the real data that it has been trained on. And these networks have seen a huge success in image classification. You see here, this is from one popular paper where they trained on a celebrity data set. And then they generated fake celebrities, so to speak. So they generated these guys here that are not real humans, but they do look very much like real humans. And in language modeling, a similar idea in natural language processing is language modeling, where you want to generate text. So you do not generate an image, but you generate text, and of course, you could also use these generative adversarial networks for this. This has not witnessed so much success in NLP, but instead there are different architectures in NLP that are being used. So traditionally, we had a recurrent neural network as a model to generate text. But now in recent years, different architectures have come up, like the transformer model, that are pre-trained. So this is also a recent innovation, that you pre-train these neural networks on general data. So you find good initial solutions for these neural networks by exposing them to the whole of the web. And if you do so, you can get language models that actually perform, or you can get neural networks to perform quite well. And in the particular situation of language modeling, they can actually produce text that is quite convincing and much better than what we have seen previously. If you want to try that out, then you can go to that web page here, and you type something in like, this course is really, and you try to have the network complete your text, and you find that in this case the result is not very convincing, so you try it out another time and it will generate for you. This course is really interesting for students interested in project-based learning, or if you are just curious about neuroscience and our limbic system. And as you can see, this is a very good summary of what we have been talking about. And so we stop here.